Good morning, students. This is Arvind, Assistant Professor, Department of EEE, DBS Kavali. So, in the previous session, I discussed about some torque equation of DC motor and different types of DC motors. And now, in this class, I'm going to discuss speed controlling methods of DC motor. Okay, so this is very important topic in this chapter. In the exam point of view, this is very important. So let's get into the point, that is speed control methods of DC motors. So firstly, before going to this one, speed control of DC motors, firstly we have to see the speed and torque equation of a DC motor. Actually, in the previous class I discussed about this torque equation, and now in this class I will focus on the speed equation of a DC motor. So actually, for a DC motor, the speed equation is obtained as follows. That means actually we know that back EMF EB is equal to IARA. Back EMF EB is equal to IARA. Actually this is known as V minus IRA. So one mistake is there. So actually we know that back EMF EB is equal to V minus IARA. So we know that from the generators, back EMF or generated EMF EG is equal to 5P and Z by 60A. So in this case, I am equating those two conditions, that is EB is equal to V minus IR, that is the back EMF equation in the DC motor, and EB is equal to 5P by 60A, that is in the generator. Actually, in the generators, we know this equation as a generated EMF of a DC generator. So here in this one also, I am taking back EMF equation same, that is EB is equal to 500 by 68. These two equations equating here. So while equating this one, we have V minus IARA, that is equal to 5P by 60A. So therefore, from the above equation, we will write speed equation, that is N is equal to V minus IARA by 5Z into 60A by P. That is the speed equation of a DC motor. So since for a given machine, so we are taking Z, we are taking a Z, that is the total number of conductors, and A, that is the total number of number of parallel paths, and P is the number of poles. So since for a given machine these three parameters are constants, that is Z, A and P. So while taking this condition into the previous equation, that is N is equal to V minus IARA by 5Z into 60A by P. So from that equation, I am putting Z, A and P are constants. So we will write the equation as N is equal to K into V minus IARA by 5. V minus IARA by 5. So here K is a constant term. K is a constant term. Why? Because we are taking the Z, A and P are constants. So in the place of those three, I am putting K value. That is a constant value. So by using that, we have N is equal to K into V minus IRA by 5. Okay, this is the speed equation of DC motor. And one more thing is also there, that is, so the speed equation becomes N is directly proportional to V minus IRA by 5. So in the previously we have N is equal to K into V minus IRA by 5. Same we will take here. Speed equation becomes N is directly proportional to V minus IRA by 5. So I already said that EB is equal, back EMF EB is equal to V minus IRA. So in place of V minus IRA, I am putting EB here. So we will write the above equation like N is directly proportional to EB by 5. So here EB is the back EMF and 5 is the flux. Okay, so hence the speed of the motor is directly proportional to back EMF. So from that equation, that is N is directly proportional to N is proportional to EB by 5. From that equation, I am writing the speed of the motor N is directly proportional to the back EMF EB and inversely proportional to the flux phi. Inversely proportional to the flux phi. So by varying the flux and voltage, the motor speed can be changed. So by varying the flux, okay, that is phi, and voltage, the motor speed can be changed. So you already know. So whenever we change the voltage, speed is changes, and whenever we change the flux, the speed also changes. Okay, the torque equation of DC motor is given by, so you already know that the torque equation T is equal to 0.159 into phi into Ia. So from that one I am taking T is proportional to phi into Ia, that is the product of flux and armature current. So from that one I am writing T is proportional to phi into Ia. So here the flux phi is directly proportional to current flowing through the field winding. That is phi is directly proportional to IF also. Okay. So previously I am taking torque is proportional to product of flux and armature current, and here I am taking the flux is directly proportional to current flowing through each current flowing through the field when there is a IF. So that is the phi is directly proportional to IF this condition. And next I am going to for DC shunt motor. So particularly I am taking the shunt motor. So for DC shunt motor, the shunt field current ISH is constant. Okay, is constant as long as input voltage is constant, that is V is constant. So therefore flux is also constant. At that time flux is also constant. So hence torque tau is proportional to phi into Ia becomes why? Because here I am taking actually torque is proportional to phi into Ia from the torque equation. But here for the especially for DC shunt motor, the shunt field current is constant as long as input voltage is constant. Therefore flux is also constant. So by taking that condition into this one, so torque is proportional to phi into Ia becomes torque is proportional to Ia only. Why? Because flux is constant here. That's why I am not taking the flux value torque is proportional to Ia I am taking. Okay. So for DC shunt motor, torque is directly proportional to the armature current. Okay. And for DC series motor, the series field current is equal to the armature current. So you already know this point in the types of DC motors also I discussed this one. So for DC series motor, the series field current, that is ISC, is equal to the armature current IA. Okay. Here the flux phi is proportional to armature current. Here the flux phi is proportional to armature current Ia. So you already know the equation, that is torque is proportional to phi into Ia. Taking that equation here, so in this one, in the DC series motor, the flux is proportional to armature current. So hence torque is proportional to flux into armature current becomes therefore torque is proportional to Ia square. That is in place of flux I am taking Ia. Okay, that is Ia into Ia, that is torque is proportional to Ia square. So for DC series motor, the torque is directly proportional to square of the armature current, square of the armature current. And the speed and torque equations are mainly used for analyzing the various characteristics of DC motor. So these characteristics of DC motor I will discuss in the next class. Okay, so the speed and torque equations are mainly used for analyzing the various characteristics of DC motors. Okay, and next coming to our main topic, that is speed control methods of DC motors. Okay, firstly we will see the speed control of DC shunt motor. So here the speed of a DC motor is given by, so I already said in the previous slides, the speed equation N is equal to V minus IARA by phi Z into A by P. So R, we will write this equation as N is equal to K into V minus IARA by phi. So why? Because I am writing this equation as K into V minus IRA means, so in this condition the total number of conductors Z and number of parallel paths A and number of poles are constants. So in that place I am taking K value. So after taking these into this equation, that is speed equation, that is N is equal to V minus IRA by phi Z into A by P. So in that place I am putting K value, that is a constant term. So N is equal to K into V minus IARA by phi. So where V is equal to applied voltage and Ia is equal to armature current and Ra is equal to armature resistance, phi is equal to flux per pole, K is constant. So you already know these points except K value. Okay, you already know these all things, V, Ia, Ra and phi also, you already know these things, but you don't know about this K value. Okay, here K is a constant. Okay, next, so from the equation, that is N is equal to K into V minus IRA by phi. So from that equation, three methods of speed controls are possible. So from that equation, three methods of speed controls are possible. First one is by varying the resistance in the armature circuit, that is also called as rheostatic control or armature control. And next we have by varying the flux, that is the flux control. And by varying the applied voltage, that is voltage control. These three methods of speed controls are possible from the speed equation, that is N is equal to K into V minus IRA by phi. Okay, actually in your syllabus we have only two methods, speed control methods, only two possible, that is armature control method and flux control method. That's why I am not discussing the third method, that is by varying the applied voltage, that is voltage control. I am not discussing here. Why? Because this is not in your syllabus. Okay. Next, I am taking this by varying the flux, that is the flux control method, and the armature control method. I am going to discuss in this class. So firstly, we will see the armature control. So this is the diagram for the armature control method. So if we observe this diagram, I am taking the motor which consists of armature winding and a field winding. Okay. So but here I am taking the armature winding in series to the controller resistance R, that is also known as rheostat. Rheostat also. This is also known as rheostat. So it is connected in series with the this one, and next we have parallel connection of shunt field wind, and these two are connected across the voltage V. Okay, and next I am going to discuss this circuit. Okay, so here a variable resistance R is connected in series with the armature circuit as shown in the figure. So if you observe this diagram, this one, a variable resistance R is connected is in series with the armature circuit. Okay, so here the input voltage V is constant. So from that circuit, input voltage V is constant. Okay, that means the speed of the motor can be controlled by varying the resistor R. Okay, the speed of the motor can be controlled by varying the resistor R. So the speed equation becomes N is equal to K into V minus IA of RA plus R. That means here I am inserting controller resistance R. That's why the equation becomes N is equal to K into V minus IARA minus IAR by 5. So this becomes N is equal to K into V minus IA of RA plus R by 5. Okay. So by increasing the controller resistance R, the potential drop across the armature is decreased. So this is the important point. So by increasing the controller resistance R, that is rheostat, the potential drop across the armature is decreased. Therefore, the motor speed also decreases. Okay, therefore the motor speed also decreases. So this method of speed control is applicable only for speed lower than no load speed, that is the base speed. Okay, this method of speed control is applicable only for speed lower than the no load speed, that is the base speed. Okay, next I am taking speed torque characteristics for a DC shunt motor with varying value of the resistance, that is the R value. I am resistance in the armature circuit. Okay, so here I am taking one graph or characteristic diagram. So in the x-axis I am taking the torque value, and in the y-axis I am taking the speed value. So between these two parameters I am drawing the characteristic diagram for a speed and torque for a DC shunt motor. Okay, so from this diagram it is clear that by increasing the armature circuit resistance, that is RA, the speed can be decreased. The speed is decreased. So if you observe this diagram, I am represent N naught value, that is the no load speed value N naught. So here that is indicated with the dotted lines. That is the base speed. The dotted lines represents the base speed of the DC shunt motor. So here by increasing the armature resistance in the armature circuit, we have this curve. So I already said that by varying the controller resistance value, the speed is decreases. Okay. So in this one also I am taking from this figure, it is clear that by increasing the armature circuit resistance, the speed can be decreased. The speed can be decreased. So if you see, this is the base speed, and here three curves is there. One is for RA, that is armature resistance, and one is for RA plus R1. So that is by using the controller resistance in series with the armature resistance. And next I am increasing the resistance value to the furthermore, that is RA plus R2. The speed value is decreases. So if you observe this characteristic diagram, you will understand. So this is the base speed curve, and these three are the speed and torque curves for a given DC shunt motor. So here, while increasing the resistance value, the speed is decreases. This regards. First one is for RA, and second one is for RA plus R1, and third one is for RA plus R2. So here the controller resistance value is increasing, that means adding. Okay, and next, the advantages of the armature control method. So here it is a simple method of speed control. So it is a simple method of speed control. That's why this method is used frequently. Okay, it is a simple method of speed control. And coming to the disadvantages, I already said that the input power is not changed. Why? Because the here input is constant. So I already said in the armature control method also, the input voltage V is constant. That's why here the input power is not changed. That is VI. You know already power P is equal to product of voltage and current. So here the output power is EB into IA. The output power is VB into IA and input power is VI. So here the input power is not changed. Why? Because here input is constant and the output power is EB into IA. It becomes less. The output power is becomes less. Therefore, for lower speeds, more and more power is wasted. Okay, for lower speeds, the more power is wasted in this controller resistance. Okay, so while increasing the controller resistance, the power is wasted. That's why hence this method of speed control is highly inefficient. Okay, and the disadvantage of this method is that the change in speed. Okay, and the disadvantage of this method is that the change in speed. So with the change in the load, it becomes large, the speed will be decreases. Okay, that is the disadvantage of this method. Okay, and next coming to the next method, that is flux control method. So if you observe this diagram, I am taking motor. It consists of both armature and field winding, but here the armature winding is connected parallel to the field winding. It is indicated here, but here the field rheostat is connected in series with the field winding, shunt field winding, RSH. It consists of the current ISH, and in the armature winding, it consists of armature current IA, and it also consists of load current IL. Why? Because this armature winding and field winding, shunt field winding is connected across the load, so it consists of the load current IL. So here we have the supply voltage V or terminal voltage V. Okay, so coming to this flux control method, this is another method of speed control of DC shunt motor, that is known as flux control method. So from the speed equation, that is N is equal to K into V minus IA RA by 5, here the speed is inversely proportional to the flux. That is N is proportional to 1 by 5. That is the inverse of flux. Okay, so by varying the flux, the motor speed can be varied. Okay, that means when we change the flux value, that is if the flux value is increased, it means the speed is decreases. So if the flux value is decreased, it means speed is increases. If the flux value is increased, it means decreased, it means speed is increases. Okay, by varying the flux, the motor speed can be varied, and the flux of a DC motor can be changed. The flux of a DC motor can be changed by changing the field current ISH. Okay, the flux of a DC motor can be changed by changing the field current ISH. So it is obtained by a variable resistance connected in series with the shunt field winding. So it is obtained by variable resistance connected to this one. So this one. So here the shunt field winding is connected in series with the field rheostat. So by using this field rheostat, so we will take the flux of the DC motor can be changed by changing the field current. Okay, so it is obtained by variable resistance connected in series with the shunt field winding as shown in the figure. Okay, and next, by varying the field circuit resistance, that is rheostat, the shunt field current can only be decreased. Okay, by varying the field circuit resistance, the shunt field current can only be decreased. Okay, next, thus motor speed can be increased by decreasing the flux. Okay, the motor speed can be increased by decreasing the flux. So I already said that previously. In this case, speed is inversely proportional to the flux. That means motor speed can be increased by decreasing the flux. So this method of speed control can be used for increasing the speed of the motor above its rated speed. That is base speed. So in the previous method, in the armature control method, the method of speed control can be used for decreasing the speed of the motor to the below its rated speed. below its rated speed. But here in this case, this method of speed control can be used for increasing the speed of the motor above its rated speed. Okay, that is, this is also known as base speed. Okay, next here the field current ISH is less, there is the field current is less, therefore the shunt field rheostat has to carry only a small current and I square R loss is also less. So here in this case the field current is less, that is ISH. Therefore the shunt field rheostat has to carry. Why? Because the field rheostat is connected to the shunt field winding only. That's why here the field current is less means the shunt field rheostat has to carry only a small amount of current. That means here I square R loss is also less. So, but this method of speed control cannot be used to obtain large variations of speed. Cannot be used to obtain large variations of speed. So, coming to the speed torque characteristics of a DC motor for a variation of field current. So in the previous case, I am varying the resistance in the armature circuit and controller resistance. But here I am I am drawing the speed torque characteristics curve for a DC shunt motor for variation of field current. So in the previous case, I am using the controller resistance, but in this case, I am using the field current. So if you observe this diagram, the characteristic diagram is drawn between speed and torque. Okay, the torque is taken in the x-axis and speed is taken in the y-axis. So if you observe this diagram, I am taking the speed. So if you observe this dotted lines is here, that is the base speed of the DC shunt motor. And here, by varying the shunt field current, that is ISH1 and ISH2, the curve is drawn between the speed and torque. So here the curve is drawn above the rated speed, above the rated speed. In the armature control method, the curve is drawn below the rated speed. But here in this case, I am drawing the characteristic diagram above the rated speed. Okay. So this is the explanation for the speed controlling methods of DC motors. Okay, armature control method and flex control method. And one more method is also there. That is the voltage control. But in your syllabus, that method is not there. That's why I am not discussing that method. Okay, thank you.